I'll be ducking behind you whenever is appropriate.
Good evening, everyone. So welcome to another ASG talk, and thank you for showing up. I know it's hard at these times, and it's good to be out, isn't it? So we are here tonight to listen to Peter Beasley, Technical Director, and Dimitri Wolenkin-Evans. Did I do a good job?
Yeah.
Senior Structural Engineer from Becca. Dimitri is heavily involved in the construction monitoring activities for the new building, university building B201. And Peter is the Technical Director and Project Director from the conception to construction of the building. And yeah, we will have a QA at the end, I'm pretty sure. And yeah, enjoy the talk. Thank you very much, guys.
Probably best if you start. Yeah, thanks for coming, everyone. We'll jump right into it.
So I guess we'll do a bit of a tag team on this presentation. So we'll just kind of touch on stuff that kind of crosses over a bit more with each of where we've been operating on this project. But yeah, see how we go and ask us any questions as we go.
Yeah.
All right. So. I guess we just start with a little bit of background on the project. So starting with a bit of a hero shot, this is kind of what the finished product's going to be supposed to look like from Simon Street. So obviously a big feature of this is the kind of vaulted timber ceiling, which is covering the current lecture theatre space in the courtyard. Yeah, let's get into it. So how do we... So I thought I'd just start with a bit of a slide around, I guess, some of the key features of the building, maybe less so from a structural perspective, and more sort of, how the project itself actually came into being. So for those of you who don't know much about the project, it's 22,000 square metres, and it's basically an adaptive reuse of an existing concrete moment frame building. It was built in the 70s by the current builder, which is Hawkins, so there's a nice little connection there to them. So the scope of works is basically a new façade, got a whole new hearts and lungs in the building, so new services, new risers. We've got an entirely new internal layout to the building. There's new lift banks and circulation nodes. For those of you who know the building in its previous life, it was a real rabbit warren. You can kind of head down one floor and get completely lost and have to come back out. And so there's a lot of kind of circulation issues with the project or with the original building. One of the key parts, obviously, from a structural perspective, is the seismic strengthening for the building, and we took what we call a light touch to the seismic strengthening to kind of target where we're going to have our interventions. Obviously, the new Atrium is a key feature. It's a whole new steel frame and timber structure over that space, and there's an extension to the level 7 of the north building, which is predominantly sort of plant areas and things like that. So I guess it's an interesting journey for the project. So we started out, I think it was in 2019, where originally this was intended to be kind of a light touch, liquor paint sort of project, and a fit out for the relocation of the education and social work faculty from Epsom into the city. So we're going through the process, and kind of as we got into the building, there were a number of sort of issues with that approach. I'll go through a few of them, but one of the key ones was really the façade of the building. We'll talk about that a little bit later. Obviously, the sustainability is a huge part of our industry and our lives at the moment, and is going to be more so in the future. The university is really embracing that, and this is adaptive reuse is a great way to kind of make sure we're not throwing those materials into the landfill. So I guess I really like the structural aspect of the sustainability story, but there's a whole lot of other things that are kind of shown on that slide. Hopefully you can read those, but things like high performance facades and rainwater capture, PV cells and things like that. So yeah, maybe we won't go into all of those, but it's just a brief sort of snapshot.
Yep. I'll just give you a quick overview of the structural scope by marking this up. So Simon Street, where you walked in from, is there. What's getting built is this new atrium. That's what you saw in that render. There's a bunch of steel plant rooms and 1.5 new floors for HVAC and all that other stuff. Same thing on the top of this tower, just there. And another great piece addition here is some lifts and stairs to make circulation a whole lot easier. And what's not really easy to see here, but did take a bit of work and should be appreciated, is all the facade panels coming off and new facades coming on, which is the first thing you see when you're greeted by the building. I'll briefly explain the lateral system so that you know what's going on. So level 8 is shown here, and the north tower each way is moment resisting frames. Fairly simple. Same thing with this one here, east tower, moment resisting frames both directions. Up above is steel portal frames and cross bracing for the new stuff. Level 6, much the same for the towers, but the atrium, that's where the atrium roof is. You have portal frames in this direction made up of steel box beams, large box beams, and large CHS columns. And in the other direction, you have some cross bracing. So that's reasonably straightforward, but the roof gets interesting. You'll see that coming up later on. Level 4 is the common floor between all the buildings. That's a podium floor. So they all share the movements and forces across there. And you'll see later there's a bit of strengthening happening in there. Below each column is typically a pile and some ground beams framing into it. And generally below level 4, it's mostly concrete shear walls in various locations with some moment frames in some places. Gravity system is pretty straightforward, so in situ RC slabs, beams and columns, and the new stuff is generally confloor slabs with steel beams under to keep the weight down.
I think just, I might just pipe in with a few lessons learned as we go through. So one thing with older buildings, they really have optimised the rebar for the occupancies in that situation, so you need to be quite careful that you know, your loading is going to be the same, and also there's a few instances where we found identical beams but with different rebar, so we suspect there might have been a mistake in the original thing, but you know, maybe don't assume that one beam is typical for other situations. So yeah, a few things that we picked up.
Yeah, it does vary, doesn't it? So talking about the design phase,
so maybe I'll just start. So this is kind of where we started in 2019. So for those of you who don't remember what it looked like, that was kind of it. It's a very kind of brutalist concrete structure, big heavy precast panels. One of the key issues, as you can see on the far photo there, is heavy corrosion in the panels, which was likely due to some admixtures in or accelerant in the curing of those panels, and also to do with the exposed aggregate and introducing cracks into the surface. So there was some really quite severe corrosion in places, and we're sort of scratching our heads trying to figure out how to do this when there was a report from another consultant 15 years earlier that said these are sort of reaching the end of their life, and so we're trying to think, okay, how are we going to deal with that? I think I guess a few other things to talk about. So the PC panels, obviously they're quite heavy. The other thing was that they had slotted connections that weren't quite sufficient to allow movement for our expected interstory drift. So these actually also happen to be one of our critical weaknesses in the building. So I guess the gears started to engage that perhaps there's an opportunity to do something a little bit more drastic with this building. So if you, and basically where we ended up was by taking these panels off the building, we firstly would deal with that durability issue. It also gives kind of a weight benefit for the building. So there's quite a bit of mass there that we actually used to offset other things that we've done to the building. Obviously the distribution isn't identical, but it's kind of nice in principle. And it also gave other disciplines the ability to really enhance the performance of this building. So they've put on a high performance airtight facade that they're actually going to be pressure testing during construction, which I understand hasn't been done before in New Zealand, so that's going to be interesting. So they're going to basically pump a whole bunch of air in at the ground floor, and hopefully it doesn't leak out too quickly. And then things like insulation and stuff like that. So that was really, one of the key sort of moments in the project, I think. And then I guess beyond that, there's things like heavy ceiling tiles in the existing building that we're sort of trying to think. If you're doing a lick of paint, it's very difficult to just kind of take a few of these out. You sort of where do you draw the line in this project? You really take it through the whole egress pathway, and so there was sort of all these kind of decisions that kind of led to different to the solution we ended up with. I think it's probably. One other thing I sort of wanted to say was, I guess, as you kind of go down this route, at a certain point you kind of got to commit. So you've got as much information as you can gather from the information sources you have, like the drawings. We did a limited amount of intrusive investigations, and ultimately you kind of need to make a judgment call about what you think you can make work, and that's kind of where we were in 2019. So maybe just the next slide. So I guess this, very briefly, this is something that we produced conceptually to kind of communicate to the client how the building was expecting to perform over a range of different earthquakes. Basically, what is the hierarchy of failure? So I guess it's not precise, but it's a good way to kind of talk about what happens to the building, and most importantly, what does that mean for the retrofit scheme? So you can see there's things like there's a bit of damage at low level intensity, and then first thing that goes are those precast connections that I talked about. Then we were starting to. The next thing was the diaphragm, and then the walls, and so we kind of trying to find where's the sweet spot for strengthening this building and not overcooking it really.
All right. So one thing that was immensely helpful during design and then during construction again is all the on-site testing and investigations that people did before I joined in. I can't tell you the number of times I've re-looked up the concrete strengths, the rebar strengths, the blockwork edge conditions, and all the stuff that was obscured. It really cuts down the amount of assumptions you have to make. And one thing that might be unexpected, but not unexpected once you think about it, is all the undocumented penetrations through shear walls that just naturally occurs through the life of the building.
Lovely services engineers. I mean, there's a lot of things that we kind of had to make a judgment call on, right? So, for example, we couldn't see the edge of the slab until the panels came off. So there was sort of various different uncertainties that we kind of had to make a judgment call on, and there was some intrusive investigations we could do in some areas, and others we couldn't because there was asbestos, and so yeah.
Yeah. So whatever you find out is super helpful, and document. And then, so I guess in terms of design, this is level 4 that you see here. So after all that analysis, we had to figure out what to strengthen and where. Is there a pencil here? There we go. So because we've taken out a chunk of a chunk of structure here for the new circulation node. We've replaced some of that capacity with a new tie across there on this podium level, because there's quite a bit of earthquake going up and down the page. This next slide, I'll just go through some of the details that I found interesting. Next slide is on this grid C shear wall, where we adopted a similar approach to the previous one, where we looked at the analysis output to figure out where the hotspots are. We figured we need some tension capacity here. And also intuitively, you'd think about putting a tie across this level, because you have a number of short sort of columns. Sorry, this thing's jumping around. Short columns and short walls that need to transfer all that podium level loading from there down into the foundations. And you're actually getting hit with that twice, because there's a whole lot of holes in here as well. No guarantee you'll actually infill all of those. As an example, these ones on this level are actually kind of difficult to access. So you sort of get what you get and do your best with that. And CFRP really came in handy here to spread the loads across the wall. So another bit of design was, so on the level 4 slab where you come in from the street, it's actually a big open space, and underneath it is another big open space, which means rather large spans for these beams, concrete beams. And the concept there is you don't need to read all of that, but the concept there is basically to make the beam section a little bit taller by taking advantage of the new slab that's up on top. That does help your negative capacity. It helps your positive capacity a little bit. So in addition to that, there's also some CFRP on the sides for positive bending as well. The interesting one here is the decision you make as an engineer. Do you say that this rebar that you're drilling epoxy in, do you use rebar theory, which says you need to drill this deep, or do you use anchor theory, which says this deep, or do you use lap splice theory, which means you have to drill that deep? Interesting debates about that one. I think we got it right in the end. I'm happy to walk on that floor.
Yeah, I guess that floor's quite an important space for the university, because there's going to be all sorts of functions and things in that space. So talk about stages and
yes,
hopefully not O-week parties or something like that. But yeah, there's going to be certainly quite a big load, and obviously this new slab that we're putting on over the top is a bit of dead weight as well. So.
Yeah, exactly. We've mitigated some of that with you don't have to build up the whole thickness. You actually can get away with some polystyrene infill as well, which is great weight saving measure. This is an example of something that looks like a simple change during design, but it actually has some downstream structural effects you got to think about. This is a floor plate on a bunch of levels in the North Tower, and essentially what's happening here is the floor is getting cut out for some new risers. On first glance, you might think, well, cool, this thing is spanning this way, so I'll just cut that out. Who cares? Job's done, but not quite, because when you do that, and this is our solution here, you actually lose a bit of backspan. So if you think about the bending moments across this red line here, you have a number of continuous spans, and then the last one has more positive bending because it's a end span. So because this was designed when people optimized things a bit more than today, you would have had more positive rebar here. And once you cut this span off, this becomes the end span. So you need more positive reo that this thing here wouldn't have had. Hence the CFRP solution there.
Yeah, there's a few little fish hooks with some of the curtailment in the existing RC was a bit short of what we'd expect as well. So there was when you look at your capacity diagram, there's little gaps. So you sort of got to make sure you can bridge that gap. So that was a little trap.
Yeah, that was an interesting one. The other one in the same tower, so this cross-section here, grid P, because this is a roof beam that's what used to be a concrete roof, but now becomes an occupied roof, so it has higher live loads on it that you got to take care of. This needed strengthening, and the way that checks and design works when you add CFRP, which is what we initially thought we wanted to do. That's what we designed here. So CFRP here, and that nib detail you saw before. Sounds great. We've asked for some propping, because one of the checks for CFRP is the existing rebar can only go to some stress level. If it goes above that, the ACI guidance doesn't like it. So there has to be some backup resiliency under SLS loads, or one of the criteria is like that. So the request here on the drawings was to please prop this thing, and you can see how intrusive this is, because at least the way we drew it, it's going all the way down. They probably could have done it with just one floor. Either way, during construction, the request was to see if we can skip that part, and we happily obliged. Because when you design this sort of thing with CFRP, you got to think about the dead loads and loads that are already on there, and only then you're gluing the CFRP, so it doesn't get engaged until later, unless you prop it. So the solution here was to use a different software that lets you check the locked-in stresses, and in the end, we went with some steel plates on the side of the beam that were tolerant to that sort of thing. This here is a thank you note to all the previous designers, but before I got involved in CM. So they've seemed to lay out the calculations really well, which made it very easy for me to answer RFIs. So next time you're designing, I'm hoping that you're documenting it as well as you can, listing out the assumptions, the load parts, and all the utilization ratios, because RFIs are coming in quickly and people want quick answers whether they can or can't do things. So one thing that keeps getting redone during construction is all these drill and epoxy and mechanical anchor details. If you have a nice copy of your calcs that say what the eccentricities and what the loads are, it makes your life easier, because you'll design this thing a few times. You'll design it when you design it, then there'll be an RFI saying, oh, can we skip these and put them somewhere else? You'll redesign it by looking at the assumptions and calcs again, and then the thing that's built is different still, so you have to calculate that once again. If it's documented well, it's a much smoother process. This is one of the more complicated connections in the atrium. So we've got those box beams that span a fair distance, and they land on these CHSs. You can see a bit of the cross bracing going in the other direction. So this is a very important knee joint for moment transfer. And what happened there was a sequencing request to from the builder or from the fabricator, because they've asked if they could just do this green part, because that makes it a whole lot easier for them, and this blue part. And I was at first stunned with how do I even answer this, because now I'm missing this bit and this bit of full strength butt welds. That doesn't sound like it's capacity I want to lose. But as it turns out, by going through previous documentation, it explained it really well, and chatting internally, of course. Yeah.
Obviously, the complexity here is changing from a square shape into a circular shape.
Yeah,
for
yeah.
a moment join, and trying to make sure that force is going to behave itself. So yeah. Interesting challenge. Yeah,
interesting point they raised when we saw it. This one was plenty of fun for me. So in the atrium, the roof is like a crinkle shape. So you get a whole lot of rafters coming in this way, then going out this way, then going down this way. and there's a whole lot of moment that is there in the static case and also in the earthquake case as the thing acts as a diaphragm. And what's hard to appreciate is, so there's a very simple request from the architect. Can we please have this thing vertical? Which sounds fair enough. And all they're doing is they're trying to hide all the steel and all the timber, because you don't want to be able to see any of the steel behind any of the facings. So these things here are purely glulam, and these bits of steel have glulam around them. This is pretty hard to do from first principles, and even if I had the loads, I did have the loads, and I still struggled to figure out how's this possible to fulfill this request. And what came to the rescue was a finite element model that someone had helpfully done before me, and I was able to just tweak the things until that was sorted out, and it told me the answers I wanted. Until the rainbow plot was green. Yeah. So this is the atrium roof that you see from Simon Street. You've got that crinkle cut. Things jumping up and down like my heartbeat. You've got the crinkle cut roof, and the forces when you go from left to right. This thing's engaged in bending across it. So some of these bits in the roof are steel. There's maybe less than 10%, maybe six of them.
Yeah, sort of quarter points.
Yeah.
On the big box beams.
Yeah.
It's not a particularly efficient structural shape.
Yeah.
The whole thing's trying to spread like this, and one thing under gravity, but seismic or lateral loads, this all tries to kind of distort. So we were having real issues with timber connections trying to take this sort of moment, particularly through the apexes and things. So we decided pretty early on to introduce some sort of transverse steel portal frames, steel frames, just to kind of stiffen it up and make sure that we're not trying to do too much with the timber connections, because that's potentially a bit of a rabbit hole.
Yeah.
So
So the design of the glulams is not particularly a big drama. It's just bending, shear, and all the other stuff that you know and love. But the end connections take a bit of thinking. There's multiple different. First of all, the geometry is interesting. So if you look at it in 3 dimensions, you've got miter cuts on different axes, and you've got router cuts also on different axes. So it's pretty hard to visualize in your head. Not shown here, but there was another example where I think one of these dowels, maybe this one here, was actually quite close to the miter cut, and you don't appreciate it on the 2D that's on the left here. You end up with an edge distance that's quite close. Again, hard to predict when it's this level of angles. But this is a standard connection across the whole roof, so you want to make sure you get it right. And I'll show you what we did. So during construction, a mock-up was made, which is part of the, and this was immensely helpful, which was part of the box beam. See on there? The beam itself has got facings on it, and then not attached in this case when I was there, but these are the flitch plates that go into the glulam members. And what was requested was a RFI. Again, sounds simple, but it triggered maybe 2 weeks of calcs. This 16 slot, they asked, can we have an 18 slot? And then they say, can we have a 20 slot for tolerance, so additional tolerance. You might appreciate, because it's 2 different trades that need to interact with each other. So any slack you can provide here is very helpful. So when designing this timber connection, there's a few things that are kind of interesting. So one is there's a number of competing failure modes in there. So some of them are more ductile than others, and you want, in some ways, a hierarchy between them in some cases. But there's also some judgment calls you make based on literature you read, and how much you believe it's going to be a problem for this particular connection that you're designing. So, for example, these big bolts with the washers, that's so that the two bits of timber don't spread apart, because the dowels aren't doing that. The other judgment call is whether you put in reinforcement screws this way or not. Again, the dowels do induce some sort of moment in that connection, so you have to think about that. And the other clever thing, I don't know if I'm giving away IP here, but these holes are slotted in this direction to reduce the moment in the dowels and that end connection region, because even though we'd love for this to be a pin, it still attracts some bending inside it.
Yeah, I guess the other part to that is just shrinkage in this timber and recognising it's not a geometrically stable thing. So you just need to think about how that change might impact your detailing as well. So.
Yeah. It's that. This is not my work, just presenting it. One of our colleagues did a very good job on the staging and sequencing of the box beam, how it's propped. There was even a whole lot of modelling in Strand 7 to figure out what the locked-in stresses are going to be, and the sequence here explains how do you piece it together to minimise the locked-in stresses, particularly in the glue lambs and the timber, because the less in there, the better. And there's some interesting effects on this thing, because you can see from the side view, it kind of wants to take some gravity as well off the box beam. So the box beam, you want to take the gravity because that's steel. But the whole thing is also a giant truss. So to that end, there's some slip connections at each apex, which is essentially just some shim plates in between these two, so that when the whole thing sags down, you can pack it out with whatever's left over with plates, is the idea. All right, it's designed, now we're building it.
Cool. All right, so maybe just some pretty pictures. So this is as of last night from site. So a couple of glamour shots there. So we got the facade. This is looking from Wynyard Street on the top left-hand corner, and this bottom left-hand corner is from what will be the new atrium looking east, and then obviously the right-hand side we've got the timber coming in. You can see we've sort of got these shapes here. So this is actually one prefabricated module, and I forgot to show a photo of one of these modules sitting on the truck, but it's a bit of an awkward shape, but basically these are all identical across the whole roof, and they've been going in quite nicely, which is pleasing. And I guess the big thing here is actually we've got these box beams which are spanning in this direction. They're constructed at a preset, and ideally we want them to come down flat once all this weight's on, and then we build the gutter. So fingers crossed that all works out and we don't have a puddle up here. But yeah, seems to be kind of tracking as expected for now. So yeah, again, some more images of the current progress. So yeah, really happy how these modules are coming in. You might have noticed from the detail that Dimitri showed, these are kind of like basically just a bearing connection. So the whole module comes in and just loads straight down on top of the box beam, and then the bolts are torqued up. So has been going in really quickly, and we put a lot of thought into making sure that was going to be the case. And this on the right hand side here just shows how complex that sort of really acute angle is in reality, but it also shows how cool that's going to really look. I think when you walk into the space, it's going to be really quite awesome experience. So really looking forward to having that. And maybe just a couple of quick shots from current state on the inside. So this is the large HSB lecture theatre, so that's underneath the atrium there. So these are the big beams that we're strengthening, and the new lecture theatre, which will be constructed out of CLT bleachers. And just a bit of fit out going on with exposed surfaces, so all coordinated to a pretty high level in the design phase, and large format teaching, so building up lightweight floors on top of the existing concrete. And another little aspect, I guess, just to bear in mind, using these old buildings and putting in new HVAC and services. The plant rooms are really tight. They're not designed for the sort of level of comfort that we expect these days. Maybe we're getting soft, but the plant rooms are really congested, and it's just something to bear in mind when you're trying to fit secondary steel in to support plant and that sort of thing. All right, is this you, Dimitri?
Oh yes. This is a type of connection that seemed to have worked well after some requests from. Was this an ECI?
Yeah, so maybe I can talk about this one.
Yep.
So basically, we did have some ECI input from the contractor, and one thing that we're very mindful right from the very start is, okay, we're going to be drilling into some existing concrete, and we're going to hit some rebar. What are we going to do in that case? So the idea was that we basically oversize the base plates and provide sort of multiple extra holes that they can choose as an alternative. So the theory being that if you hit a bar here, then hopefully you kind of got a gap here, and vice versa in this direction. If you hit here, you can miss here. So all good in theory, and it did work pretty well in most cases, particularly when we were able to offset or deliberately offset from the grids. So for the circulation node, for example, we were connecting with these big new structural elements. We deliberately kind of offset things so we could get our big diaphragm drags through less congested areas, but it's not always possible. And I think the other thing we were kind of relying on the contractor to do a lot of scanning and locating of rebar, and it's a bit hit and miss, no pun intended, but I think often you pick up one layer of rebar and miss the second. That's sort of a little bit deeper. So yeah, that was one of the challenges on the project, but I think generally it's worked pretty well. Yeah, and I guess you just be mindful of trying to protect. I mean, we're effectively custodians of this old building and trying to make sure that the contractor doesn't wreck it. So just keeping a close eye on how they go about things is really important.
Mm-hmm.
Okay.
Yep. Something that was interesting for me was on one of the things that I came across was services seemed to go where they wanted to. So during the intent was there's a floor that we have that is a number of bathrooms going on there, and behind is like a services corridor. And initially the idea was for all the pipes to go down through this big giant hole and just disappear. That was the ideal, but in real life, there's other drivers than just structure. So what happened is you go have a look at a drawing. Sorry, I'll erase this stuff. It's confusing. And you actually end up with holes that sort of, this slab is spanning this way, by the way, that sort of interrupt a whole lot of my my bars across here. So there's chunks of slab that doesn't have as much rebar as I would have thought. And if you think about why that's done with services from their perspective and from the builder's perspective, it makes a lot more sense. Because rather than going through a hole which is not fire rated, it's easier to go through existing concrete, and then your fire collars and stuff are on here. And that's all separated. And the other thing to appreciate is that this stack of pipe, it's much easier if it's one big straight line that doesn't do a whole lot of doglegs going down. So if asking for them to miss rebars on each floor is tough. So yeah, that was something for me to note. And we've strengthened that a little bit, this particular instance. And in most other cases, it wasn't this congested. And another thing that I've learnt is facade seems to be more important than structure. But basically, it's easier to modify existing structure than go order a new facade panel or try to refabricate some piece of facade that has like some long lead times. So you can see from this one shop drawing, they'll have some dimensions that they can't move on, like that's 110 critical, and they'll have probably not shown here, but they'll have like clearances they want to be away from your structure. I can't remember why. I think there's some tolerance that's required for their thing to perform properly. You can see the level of accuracy. It's a 604 millimeters, which for an existing building, if this thing is a straight line going up all the stories, the existing building could be a little bit off square or a little bit not on a lean, but sort of offset as you go up. And while for the most part this was not an issue, there were instances. So just be ready for RFIs asking you, could you please move the existing structure to make way?
This particular detail looks fairly innocuous, but I think we probably had about at least a dozen design meetings on this, just agonising over with all the different disciplines at play. You got the fire stopping minimum dimensions. You've got the tolerances for the facade in both the vertical and horizontal direction, and you've got all sorts of things that go into this, and how easy it's going to be to build. How does the facade supplier want to fix to? So we ended up with basically a steel plate that goes around the perimeter of this building, and we offered up kind of a series of discrete steel plates that the primary contractor would come through and install ahead of the facade sub, just to give them a constant substrate. So we kind of gave them a few options. One would be a series of discrete plates, or alternative was just a continuous plate all the way around, and they loved that idea, and so that's what we ended up with. I guess there was a high degree of repetition with that detail. They were able to just go ahead off the critical path and kind of get that edge nice and ready to receive the facade, and I think generally it's worked pretty well. But yeah, some of these dimensions are very inflexible and driven by things like the mullion capacity. You'd think, oh yeah, surely you can push that to 120 mils and it'll be fine, right? But not always the case. And in particular when you start talking about fire stopping between the slab and the back pan on facade, that's really something you don't want to be messing with. So yeah, a lot of meetings on that one.
Yeah. This one here. So, and there was a bit of inevitably you'll run into RFIs asking for alternative fixings. You'll specify one brand or one type of fixing, and either the epoxy, they'll ask for a different epoxy, either supply issues or just getting the job done quicker. And similarly for mechanical anchors, there's a point in time where there wasn't enough M20 HST3s, which caused a shortage of M20 TrueBolt Extremes from Ramset. And offered up for us was the HSL4 and the Spartex, which are slightly bigger. They've got the big sleeves around them, and they've got larger spacing requirements and larger edge distance requirements. So I guess, I don't know, for me, if I'm designing, probably in the future I might even if I'm specifying HHC3s, I'll probably space them further apart in case I'm asked to use the ones that have the larger spacing differences, just in case it comes up as a question. I think we're not done with shortages. And you can provide some helpful notes to the contractor so that they can do the research for you on what E-tag, EOT, and all that other stuff. Yeah.
I think one thing I didn't mention is really the program on this project has really been one of the key drivers for the whole thing. And we've been from 2019 to now, it's been pretty fast track. So we're really trying to keep the contractor going and not getting hung up with containers stuck in the Suez Canal and stuff like that. So very mindful of that sort of thing.
Yeah. That's weird. Almost on time. So I'll probably run through a few things that stood out for me while I was on this job. If you reuse a building or parts of a building, I think you're unlocking great value, and I think you're doing everyone a service because you get most of the structure for free that's already there. I think that's a great thing to do. If you write a good DFR instead of calcs, that's immensely helpful for the next person that's doing the CM. The RFIs get turned around much quicker. Don't forget gravity and all the simple changes that might trigger some sort of strengthening requirements, like we saw in that riser example with the backspans. That applies to beams as well, if you demolish beams. I guess this is your one.
Yeah, I think there's with the old drawings of this building, there's so many little nuggets of gold in there. So really important to get into those drawings and kind of pour through them and read every little handwritten note that's in there, because there's all sorts of good stuff. And I think one of the key things is I guess taking that with a bit of a grain of salt as well, and applying a judgment lens to it. There were sort of instances where we suspected that the original designer hadn't or had missed something, or in fact there were instances where we thought there were piles under a part of a building but they weren't on the drawing. So from a judgment perspective we kind of allowed for that, but they weren't kind of explicitly shown. And I think the other key thing is to really understand how the building's behaving and hone in your intrusive investigations on those key aspects. So we did things like demolishing a portion of the diaphragm, the shear wall connection, just to get some confidence around the detailing of the starter bars and make sure that they were terminated correctly within the shear wall. All sorts of things. Durability tests of the concrete, making sure there's no chloride ingress, carbonation, and things like that. So those are all sort of things that we kind of picked up along the way, and the sooner you can do them, the better. Can kind of inform your decisions, design decisions. But that was really important.
Yeah, I think that's us.
all I can think of.
Yeah, we certainly have time for questions, if that's the program.
Yeah, obviously thanks about Peter and the entry. We'll
Yeah.
find a few minutes for questions. Anyone got any questions? Okay, that's pretty silent. I've got a question. So when was the original building built?
It was 1970, I think.
Okay.
So kind of probably quite a good decade if you're going to try for adaptive reuse. I think you might want to think twice if it's in the 80s. But we had reasonable confidence that it was going to be done to a reasonable standard, and hopefully not too many shortcuts. So I think that's just something to bear in mind.
Yeah. So in terms of the intrusive testing, what sort of consistency do you see between what's documented on the drawing in terms of material compared to what you see on site, like reinforcing strength and concrete strength?
Yeah, there was a bit of variability actually. So some of the concrete was a bit not as hard as we expected. I mean, we've done many projects along this road of similar sort of eras, and some of them were extremely hard concrete, particularly the Ministry of Works ones. This one, maybe had a slightly lower batch dosage of Portland cement or something, but it was still good enough for what we needed. So, but it was really good to kind of get that information, just get some confidence that we were dealing with some good bones, and particularly the rebar I think came out better than what we expected in terms of yield strengths and things like that. So I think a lot of the guidance is probably a little bit on the conservative side, and I guess it's just to do with having a comfortable margin, I suppose, on making design decisions. But yeah, so that was kind of really useful. And I think we did obviously kind of tests around the durability of the structure to make sure it's good for another 50 years. So making sure that there's not really high levels of chloride in the concrete, particularly in the foundations when it's been in contact with moisture. So yeah, it's sort of kind of in the mix.
Would you really go into a bit more detail about how you test durability to justify the building to last another 50 years?
Yeah, so we basically went around the building and used a bit of judgment around what sort of areas would be kind of hot spots. So like I said, the foundations, there's particularly in the near surface, there's moisture and there's oxygen, and very difficult to do some sort of remedial measure if we did find an issue. So that was one area we targeted. We did some in the superstructure, and basically I think it was EQ Struck or WSP did the actual lab testing for us. So they did a really good job. But yeah, it's kind of just a judgment call and get a reasonable sort of representative sample across the building to get some confidence in it. But the good thing was that once you take the façade out of the equation, the rest of it was actually really good, which was quite reassuring. I think what had happened when they made these precast panels, that they had some sort of admixture to accelerate the curing or something that had raised the chloride levels in the mix, and it's sort of a systemic issue with that particular feature on the building. So yeah, it's quite. So I think I kind of like how the facade tied in with the whole sustainability outcome for the building. One thing I didn't mention is that I guess the whole building has received a 6-star Green Star rating for the design portion. I think it's from the Green Buildings Council, it's the highest rating that's been achieved in New Zealand so far. So it's a really awesome achievement. I guess the structure is only a small part of that, but it's nice to contribute. And I guess going through the construction now, the seems to be all on target. But there's points, like I said, for things like pressure testing of the facade and diverting waste to landfill from landfill and that sort of thing.
So actually, I'm going to ask too many questions, but just wondering with Green Stars, obviously I'm involved in the project. And obviously, we're using the existing structure. Would you get some Green Star points with?
Yeah, there is a special point that you can apply for. But to be honest, the Green Buildings Council, the framework for an existing building isn't that. It's really tailored towards a new building. So I think in our instance, we kind of had to appeal to go back to first principles and demonstrate, okay, how does this compare to what might be a kind of a benchmark new building, for example, and talk about some of the methods that we used to maximise the I guess the potential of the existing fabric in building. So we didn't sort of stop at just a simple force-based sort of number and make it too easy. So yeah.
Thank you very much. Does anyone have any questions?
Quick question. Thank you very much. The structure has 3 types of basically concrete, steel, and timber. seismic loading is, and ductility is very important. Which number you assume for seismic?
I can't remember exactly what ductility, but I think it was, I think for the Atrium, for the new build parts, we were going for effectively nominally ductile. Certainly for the new extensions on the building, I think it was effectively elastic, because you don't really get any benefit for saying it's new at 1.25. You're still going to go through the same detailing really, but I think it was kind of the elastic parts loading, so it was fairly basic from that front. But I guess we did a pushover for the existing seismic capacity, so I guess you can kind of infer your ductility from that. I guess the answer is there's a range of ductilities. But it's not, like as you mentioned, it's not straightforward. There's actually effectively 3 different superstructures and then one common podium, so putting all those together is quite an activity. But,
So we've got time for one more question.
Thanks, Sebastian. I really like your solution having multiple sets of walls in the same base plate too, in case if you were to hit rebar. However, I see some challenges coming with that. How do you deal with the weakening of the plate? How do you deal with the number of combinations possible? Are we putting like the rebar on the 2 set of walls on one side of the beam, or it's an infinity solution?
yeah.
And did you get any pushback about the extra holes which are to be done by the manufacturers?
No, well, actually, the instances where we used this detail, they were, I guess, in fairly, how do I put it, gravity load situations where we had, kind of not extremely high loads. So we effectively had a sort of an envelope type approach where you sort of assume the worst case kind of situation where you got, the worst, using the worst holes and the worst edge distance, and there's plenty of capacity for that. Typically for a gravity load, the loss of strength from the holes is pretty easy to allow for. So there's some more material in the plates. The request actually came from the contractor to have this flexibility, so we didn't have any issue from that perspective. And I think from an overall cost, trying to make sure that the contractor's got a streamlined run. The construction is really the biggest component. The labour, the material is perhaps secondary in that respect. So, did I answer all?
Yeah, no, totally. Thank you.
But there were certain situations where we had quite critical drag loads, for example, with the new circulation node. So we've basically got this new building that we're trying to grab into the old diaphragm. So we've got these big tie forces that we're trying to grab hold of, and those were quite difficult to do, and trying to drill through concrete beams and grab onto big steel plates. So in those sort of situations, we had to be quite strict around the eccentricities and stuff like that.
Thank you, Peter and Dimitri, for this very informative presentation. We certainly really appreciate it, and ASU would like to show a small token of appreciation for your work. Thank you so much.